5.2, continue. Whoa, that's an O, not a C. We'll call it two-way tables. And Venn diagrams. America. There we go. All right, so the first two-way table that you actually, I'm going to go ahead and do the alternate examples. Look at that. So, hey, let's look at this. We have score. And we've got a probability. So what this is we found the probability of these scores, okay? On the AP Statistics exam. All right, there are only 5 particular scores that you can get. The probability of getting a 1 is 2.235. Probability of getting a 2 is 0.188. Probability of a 3 is 0.249. Probability of a 4 is 0.202. And the probability of a 5 is 0.126.
Is this among students who take the class, or is this among students who take it?
This was randomly select. If you were to randomly select a student who took the 2013 AP Statistics exam, this would be the probability that that student got one of these scores. Okay. So, first thing we're going to do is we're going to verify that this is a legit, we'll just call it legit, I'm too tired. Then it's a legit probability model. Yeah. All right. What are our rules for probabilities? The main rule is probability's got to be between 0 and 1, right? So if I was to add this up and I was to get, an answer greater than 1,
Wow.
it would not be a good probability model, would it? All right. So let's go ahead and add them. And in fact, in this particular case, right? Every single scenario is represented, right? There's nothing that isn't represented, yeah? So then what do you think these should actually add up to? That's correct. They should add to 1. So let's see. Is it the case that 0.235 plus 0.188 plus 0.249 plus 0.202 plus 0.126 is 1. It is the case, right? So if I add those, so all probabilities add to 1. So that checks it out. Hey, let's look at B. Second thing we need to look at with this. what's the probability that the chosen student scored 3 or better? So probability 3 or better. What is that? How would we get that? All right. So we have to decide: are each of these events mutually exclusive? Are they mutually exclusive? I mean, the way that I can answer that, I could ask myself, okay, is it possible for 2 of these things to happen at the same time? No way. A student can't get both a 4 and a 5, or a 1 and a 5. It's either one or the other. So then what we're considering then is that this would be the, remember we have the rule for mutually exclusive events, that probability A or B is equal to the probability of A plus the probability of B. So what that means is that in this case we have 3 particular events occurring, right? So that's the probability of a 3, the probability of getting 4, or the probability of a 5, right? 3 or better means that each one of those things counts as a success, right? Or a desired outcome. So I could just do this then. So that would be, and these 2 things are actually not equivalent, but so I'm going to write probability 3 plus probability of getting a 4 plus the probability of getting a 5. We're going to write this down here. That's going to be equivalent to 0.249 plus 0.202 plus 0.126, which is going to be 0.577. Hey, you could also use the complement rule if you wanted to, but it would be weird. Right? You could also do the probability that you didn't get a 3, right? Which would be 1 minus the probability that you get a 1 or you get a 2. I'm going to just write that down just for grins, okay? Yeah, just for lulz. So the probability of the same way, you could also do the probability, sorry, that you get a 1, or rather, sorry, take the complement. 1 minus the probability that you get a 1. I will get it together. A 1. Or a 2, right? You could use the complement rule as well. That would be an option. It seems counterintuitive to do it that way, but it works. All right. Fantastic. Let's do another example. Huh? Yeah. All right. Ready to move on? Let's check out another example. So that is a table. Two-way table. Here, and now we're going to introduce a two-way table. And you'll see there are also examples on pages 308 and 309 of each of these things in your book. So I'm going ahead and give you guys examples that aren't in your book, so that you have as many examples to draw off of as possible. So, I'm going to call that example 2, even though I didn't label the first one example 1. We're going to call it this, okay. So now I'm going to make a two-way table. Home owner, not a homeowner. Or me. I don't own my ring. I'm going to actually go ahead and set this up as a table. That word is graduate. I am quickly running out of room. So, not. I know, I'm running on not very much sleep. And I work until 5:30. So that means not a high school graduate there. And then we have our total. Okay. And then over here we have a total. So call it a two-way table because you can read it in two ways. You could read it vertically or you could read it horizontally. We have some numbers. All right, here we go. Let's do this thing. Okay. So what do each of these cells in the table represent, right? Obviously, this is someone who is so all of these people are homeowners who are also high school graduates, right? We use this thing to calculate a bunch of probabilities, okay? And in this case, we wind up with some interesting things that come out of it. All right, so let's. And by the way, I think you probably guessed that this data comes from a random sample of 500 U.S. adults. They were identified as a high school graduate or not, and as a homeowner or not, and then we got this data. Pretty self-explanatory, anyways. So, if we were to choose from a member of the sample at random, we're going to find some different probabilities. We're going to find the probability that A, the random person chosen, is a high school graduate.
Done.
Huh?
Done.
Well, the total people that graduated high school are 310, right? The total people sampled 500. So that probability would be
0.62.
And let's call it probability that they graduated, probability that they're a G. Probability that they graduated. Sorry, probability G. Yeah, it's gonna be 310. The probability that they're a G is probably closer to 1,738. Thank you. I guess I want to catch on. Huh? Probability G. It's probably close to 1,738 or 1738. Sorry. Okay. All right, let's look at B. Yeah. I'm not scared. All right. Hey, how about the probability that they're a high school graduate is a grad? I'm trying to remember how to do this. And owns. Been a long time since I wrote an ampersand.
221.
So yeah, that's 221 out of 500. So probability G and H is going to be equal to, I don't know why I'm looking at that, and the answer is right there. 0.442. All right. And lastly, let's look at the probability that they're a high school graduate or own a home. High school grad or homeowner. All right. So we could write that as, right, we call that probability G, right? And I'm going to write all of the notation, sorry about that. So it's probability G or H. And that's the same thing as the probability of G plus the probability of H, which is going to be 310 over 500 plus hold on. Hold on a second. Are these things mutually exclusive? Is it possible to be both a graduate and a homeowner? Oh no! Oh no! No, we can't use this, right? Finally got out the red mark.
You just have to subtract them.
Yep. Okay. So, and I still need my table. So, high school grads, well, you could, or you could just add, right, you could do,
G plus
well, you could do all the people that graduated from, you could just add up all the people that do, right? So you've got 221. That's high school graduates who own a home, right? We won't have this 89 because those guys don't own a home. Yes, they count. All right, sorry, we're looking for a high school grad or a homeowner. So that counts. These guys graduated from a high school, right? These guys own a home. These guys have neither thing going on, right? So we're going to add up each of these and divide by the total. So it'll be over, I can't write properly, 500. So if you add those, then we're good. It's 429. 500. Yay! Sorry. Okay, so let's get down to what you were talking about, okay? All right? Let's talk about and Paris was talking about what to do. He was saying, hey, why don't you just subtract the things that they don't have in common, right? Or their intersection. Yeah. So we could also say that the probability of G or H then is going to be equal to the probability of G plus the probability of H minus the probability of G and H. Wait. Sorry. I put my answer there. Did I put the answer backwards? Yeah. Or did I? No, I'm so confused. I think it's... Had to write the first time. There we go. Sorry about that. G and H. Cool. So in this case, we would get the same thing. We would get 310 over 500 plus 340 over 500 minus 221. What you get? Okay, so on your AP statistics formula sheet, they do not use the word or, and they use the word and. They use some different notation. All right. They use. We're gonna talk about it. This is our segue. So we're gonna call this probability of A union B. Okay.
Oh yeah.
So A union B is A or B. That is going to be equal to, we're going to write this as probability of A plus the probability of B minus the probability of A intersect B. So that's how those things are said. So this is probability of A union B, and this is probability of A intersect B. Yeah, so now things get different. And that is the way that this formula looks on your AP statistics formula sheet. They don't say or and they say union and intersect. So that right there is a healthy segue into talking about these Venn diagrams. All right. So let's look at Venn diagrams. Please don't. All right, so a simple Venn diagram. If I have some event A, right? I don't really need to shade it. All that stuff over there is, that's awful. Okay, the shading was a terrible idea. Everything out here is going to be a complement, right? Not A. All right, we can also look at a Venn diagram like this. where I have two events, A and B, and then we'll just call this S because it's something different. It's not really, yeah, it's kind of not A, not B. We're just going to call that. Alright, so what's going on? These two events, right? So in this case, if we have a Venn diagram that looks like this, A and B are disjoint. What's another word for disjoint?
Not the same. They can't overlap.
Yep. Or they're mutually exclusive, right? So I'm going to try to use those two words interchangeably. Okay, and then the next case that we have is the case that you normally see with these Venn diagrams. That events A and B are not.
They are
Not mutually exclusive, right? They have an event in common. This event right here. And I would actually denote this shaded event, I would call this A intersect B, okay?
Would you call that non-mutual?
Don't call it that. You might get the wrong idea. No. You just say they're not mutually exclusive, or they're not disjoint. And then the last case that we have with these Venn diagrams, so just getting us into using this notation. If I have two events that are not mutually exclusive, if I'm looking at the whole kit and caboodle, where all of them are shaded, that is A union B, okay? All right. So, let's go ahead and look at our previous example and apply to it some Venn diagrams and some new notation. So I'm going to go back over here, and I'm going to scroll up and down to look at this. Almost done. 5.2 is a long one. A lot of it. And it's we're building a foundation with a 5.2. You got to really make sure that you understand this notation, because we'll crank it up and we'll use it for weird stuff. So, okay. So let's go ahead and look at a Venn diagram for this. Boom. Bam. Boom. All right, we got the probability that they own a home. The probability that they graduated from high school. Or actually, let's go the other way. Let's call this G and call this H, right? In here, I should have made it bigger. I tried to make it bigger, right? They have 221 events in common, right? People that graduated from high school and own a home. And then over here, we have 119 that are only homeowners. So let's just use this notation, okay? Using the notation. So we would say then that G intersect H is equal to 221. Yeah? how about G intersect H complement? Go back up to our table. So we're talking about people that graduated from high school and are not homeowners. Where is that? Up here. High school graduate, but not a homeowner. That's 89, right? So I'm just using numbers to get familiar with notation. That's all. This is new stuff. It's kind of weird. All right. So we've got the. How about the event? Not a high school graduate, and owns a home. So we can go up to our table and find that. Not a high school graduate, but a homeowner is 119. And then how about G complement? Sorry, intersect H complement. So not a high school graduate and don't own a home. Yeah. Huh? Yeah, that was at 71, right? Boom. So I hope you feel a little more comfortable with that notation after that. I know that's kind of the newest thing. You've probably seen a two-way table at some point in time in your education career, but maybe have not seen this notation. So there's that. So you all are ready.
Wait, when you add 71 to go to 89 and 119, it's what, like 16, or...
Not a graduate and doesn't own a home, it's just the 71. If you have or, it's going to be different. All right, there is an AP exam tip here that I was told to highlight. It says, many probability problems involve simple computations that you can do on your calculator. It may be tempting to just write down your final answer without showing the supporting work. Don't do it. A quote-unquote naked answer, even if it's correct, will usually earn you no credit on a free response question. So in other words, right, yes, it would be easy if they asked you for some probability, put it in words. It would be nice for you to write actually the notation and show all your calculations. So we talked about that already, right? We have definitely talked about it, especially when we're doing P-scores, right? That even though, yeah, you can spit it out in your calculator in a second, you have to show that calculation. So I do believe that is all for 5.2. I'll go ahead and post this on the interwebs for you so that you can peruse it at your leisure. Thank you.